Hey, here's the do now for the day. You can hit pause on the video till you got your answers. And we should get both of these. So we'll keep the same base on the exponent, log base 5. Output comes next, so log base 525 equals b. Always the answer is going to be that exponent. And for number 2, converting into exponential form, keep the same base. The base of the log turns into the base of our exponent. The exponent is the x on the other side of the equal sign from the log. So 3 to the power of x equals 9. Nice. Well, today we are looking at the inverse property in logarithms. Learning target for us will be to write and evaluate logarithms using the inverse property. Let's start by a quick refresher here. So we've seen both exponentials and logarithms before. We know that we can go back and forth, just changing the way that they are written. So I want to make two observations, point out two things. With exponentials, 3 to the power of 5, for example, the thing on the other side of the equal sign, the answer, if you will, is the output. If we take the exact same numbers and rewrite that in logarithm form, so you get log base 3 is 243 equals 5, the thing on the other side of the equal sign, or the quote-unquote answer, is the power, right? So they both end in different places, and that's going to be pretty significant for what we're looking at for today. Okay, so another chance here to do the exact same thing we just did in the do now, but with a little bit weirder looking equations. So let's start off over here on the left-hand side. Convert to log form. All right, well, this whole thing is the exponent, right? So that whole thing stays together. It's already got a log in there, and we're converting to log form. And don't overthink it. So the base is 5. So I'm going to go log base 5. Exponent. The output shows up next. And then on the other side of the equal sign is the exponent that we just put in the box. So log base 5 of 2. All right, well, we converted. So I got a question for you. I know you've never seen an equation like this before, but I'm pretty sure you'll be able to answer this. Just think about this for a second. So if log base 5 of x is equal to log base 5 of 2, what do you think x equals? It's 2. Nice job. All right. Let's look at the other side over here on the right. So I've got in log form already log base 3 of 3 to the 4th power equals x. If I convert this to exponential form, I'm going to start with that 3 that's the base of the log. So that's going to form the base of my exponent. The x over on the other side of the equal sign, that is my exponent on the 3. And then the output, 3 to the power of 4. Okay, I got a question for you about this one as well. If 3 to the power of x is equal to 3 to the power of 4, what do you think x equals? Yeah, 4. Nice. Okay, so these are both actually examples of the inverse property. If we go back to the original versions here, you could kind of say, look, the final answer was just this 2 right here, right? The 5 here and the log base 5 here like ended up undoing one another. And the same thing happened in on the green side on the right. So here's our final answers right there. And you could kind of make the argument that log base 3 and this 3 right here kind of undid one another, canceled each other out. So our answer is just 4. And that actually is what happens. So even though we have seen both exponents and logarithms represent a power, right? An exponent is a power, and a logarithm is also a power, but written in a different way. So based on the way that logarithms are written, since the answer to a logarithm is the exponent or the power, but the answer, quote unquote answer, to an exponential equation is the output, the thing that it equals is different. One is the output and one is the power. Those are the two opposite sides of what we need to get from one to the other, right? Basically, they're mathematical inverses of one another. So one is telling us you use this power on the base, and the other is saying here's the answer you get. What was the power? It's just like looking at the same thing from opposite directions, like adding and subtracting are mathematical inverses. One does, one undoes. Dividing and multiplying, one does, one undoes. exponents and logs. One does, one undoes. Right, so as long as the exponent, the base of the exponent and the base of the log, as long as those are the same, then these two statements are both true. This is what the inverse property of logarithms looks like, whether you start with an exponent on the top or whether you start from log form on the bottom. So I've highlighted the bases are the same. B is the base of the exponent, b to the power of log base b of x. That's just going to equal x. So essentially, this log base b and this exponent base b, they're inverses. They undo one another, and so x is what is left. And in the bottom one, this log base b and this exponent base b are inverses. They undo one another. So just the x is our answer. Okay, well, let's see if we can put this into practice with some examples. I got 6 to the power of log base 6 of 11. Log base 6 and 6, those are inverses. So we're just left with 11. And natural log of e to the power of 14. Okay, well, we're going to remember one thing. This will make this a little bit easier. Natural log means log base e. We don't ever write log base e, but that's what that means. So if we saw this, it would be a lot easier for us to say, oh, the log base e and the e to the power of, those are inverses. They cancel each other out. Right? It'd be visually easier, but whether we don't write it that way. We write natural log as an ln. So the natural log and the e still inverses. Final answer 14. All right. I'll give you a couple of examples here, and then here's some practice. Try these ones on your own. You can hit pause on the video, see if you decide on what your answers are, and then hit play again. All right, well, welcome back. Nice job. So this first one, we're just going to get x plus 3, right? E to the power of and natural log, those are our inverses. And for the bottom one, log of 10 to the power of 14, we just get 14. So again, it might have been more visually easy if we'd seen that base 10. So if it's base 10, we don't ever write the base, right? So if it just says log, that means base 10. We just don't write that. It's a time-saving device, right? That's just the convention. So log base 10 and the 10 as the base of the exponent are inverses. All right, let's look at something else. Next, so we got 3 different types of examples. So that we got the first one is done. Second one goes like this. So we've actually done problems like this before. We're going to evaluate log base 6 of 36. There's a number of ways we could arrive at an answer for this. For example, we did problems exactly like this yesterday using the change of base formula, and we could still do that. But since we're learning the inverse property today, I'm going to demonstrate how to do this with using the inverse property. So here's what we need. We're going to have to do a little bit of rewriting. I need this thing to be written as a power of 6 so that it will be an exponent with a base of 6, and that'll match the base of my logarithm. So I'm just going to rewrite 36, and this is supposed to be an easy one, so it's like, oh, 36, that's 6 times 6, or we could just write 6 to the power of 2. Right, well, now I can use the inverse property. I've got log base 6, and I've got 6 to the power of 2. Log base 6 and 6 is the base of the exponent, are inverses, and so we get an answer of 2. All right, same thing on the next one. Log base 3 of 81. So we're going to have to rewrite this 81 so I can get it as a power of 3. All right, so I know a lot of times people say, oh, 81, that's 9 squared, which is totally true, but not what we're after, because 9 as the base of that exponent does not match 3 as the base of the logarithm. So it's not going to help us. We can't use the inverse property. But it probably gives us a pretty good starting point. So if we know that 9 squared is 81, it's the same thing as 9 times 9. And I know that 9 is the same as 3 times 3, right? So I break each of these 9s apart into 3 times 3. And 3 times 3 times 3 times 3 again is going to equal 81. How many 3's is that? That's 3 to the power of 4. So I can change this original 81 into 3 to the power of 4. All right, now log base 3, and 3 is the base of my exponent. Those are inverses, and so my final answer is 4. Fabulous. All right. Well, there are a couple of examples. How about you try this on your own right here? A couple of problems do the same thing. A little bit trickier on one of them, but go ahead and hit pause on the video, try these out on your own, and once you get your answers decided on, you can hit play again. All right, well, so I'm going to rewrite this. Let's look at log base 2. 32 is 2 to the power of 5, and so that means log base 2 and 2 is the base of the exponent. Cancel, giving me an answer 5. And then for the second one, 1 over 27 is a little bit tougher maybe to come up with on your own, unless we remember how to do reciprocals as an exponent. So 27 probably is a little bit easier to see. So 3 times 3 times 3, that's 27, but I want 1 over that. So I can get this far. I know it's 1 over 3 to the power of 3. That's not too challenging. But then I don't actually want to have that 1 over anymore. I just want 3 to the power of something, and that'll give me 1/27th, right? So this is a reciprocal. And as you recall, we can get a reciprocal from a negative exponent. That's what negative exponents mean. So I can rewrite this whole problem as log base 3 of 3 to the power of negative 3. Log base 3, base of the exponent of 3. Those are inverses. So I'm left with negative 3. Super. All right, last type of problem. Kind of similar. This first one is actually like the one we just saw a second ago. So I'll do these as examples. I'll give you a couple afterwards to try on your own. So same approach here. I'm going to rewrite the 1 over 10 to the power of 2 using base of 10, because my log has a base of 10, even though it's not written there. That's what it means. And so the 10 is already to the power of 2, but I need that reciprocal, and so I just put a negative sign in the exponent. So 10 to the power of negative 2 is going to give me that 1 over 10 squared. And then log base 10, 10 is the base of the exponent. Final answer, negative 2. Okay. And then the last of my example problems is natural log. And so remember, ln means log base e. And so I want to write this output inside the parentheses as e raised to some exponent. All right, well, square root. That's the new thing for the example problem. We've seen square roots before. If you remember, square roots represent a fractional exponent. So I can get rid of the square root symbol and just change this into e to the power of, and then I'll have a fractional exponent. So natural log of e to the, so the square root is the power of 1/2. Right? But I already had e to the power of 3. So the 1/2 is going to give me the square root. I need to multiply that 1/2 times the 3 that was already on the e. And so 3 times 1/2 is going to give me 3/2. Right? So I've taken this output, square root of e to the power of 3, rewritten it as a fractional exponent. So now I've got the whole thing, natural log of e to the 3/2 power. This natural log means the base is e, and this exponent has got a base of e, so my final answer is just 3/2. All right, let me give you a couple here to try on your own, and then you'll be good to go. So hit pause on the video and while you work out your answers for these. All right, so let's rewrite the first one. So we got natural log of, this will be e to the -7th power to give me that reciprocal, natural log, and e are going to cancel, or they are inverses. So final answer is -7. And the bottom one here, I'm going to rewrite the cube root of 10 to the power 5. So the cube root is going to give me a fractional exponent where the denominator is 3 for the cube root. And since 10 was already raised to the power of 5, I just multiply the 1/3 by the fractional exponent times the 5 to get 10 to the power of 5/3. Log base 10, and 10 is the base of the exponent. Those are inverses. Final answer is 5/3. Cancel here, cancel there. There we go. All right. Have fun.